Alright, so as promised, let us go ahead and try to put our equations in a more manageable form that is practically a lot more useful. So this is called the Mohr circle. Now, so far we have a number of equations, and let me put these equations in a very generic form. So recall that what we had done was, in our derivation, we had taken a structure and we had concentrated on a certain type of loading, and with that loading what I can do is, using mechanics of materials knowledge, I can go ahead and calculate the state of stress. Now, that state of stress is associated with a certain point in the structure, say that point. Well, as I said, this is just a way to motivate what we're doing. It's not necessarily a state of stress I'm drawing that's associated with that problem. So at a point, I will have in general associated with it a state of stress, and we depict it geometrically in this fashion. Okay? And so at the point we are considering, there is a natural coordinate system usually that is aligned with the problem, and there is a sigma x, there is a sigma y, and there is a tau xy. And what I'd like to do is I'd like to be able to calculate how the state of stress looks at, in general, an arbitrary orientation. Now, among those arbitrary orientations, the principal orientations usually associated with normal stresses, but also with shear stresses, are of particular importance. But presently, we're just concentrating on any arbitrary orientation. So I'm still at the same point. It's just that I take different cuts, different surfaces, and so that's a different geometric depiction of the same state of stress. It's just mathematically the components are different now. There will be a different normal stress. There will be a different shear stress on these surfaces. Okay? And remember, as we are doing this, which is very important, that we have assumed that we have plane stress. That's an assumption that is on the background, always present in what we are doing so far, which means that there is a sigma z is equal to 0. So also the shear stress is associated with the z direction, tau zx and tau zy. They are both equal to 0. Okay? So it doesn't have to be the z direction, it could be the x direction, then I would have here z and y, etc. But so far, that's what I have. That's what I've assumed. If we know how to deal with the scenario, we know how to deal with anything else. Okay, so that's the picture. And remember how we dealt with the scenario. What we've done is we've taken one of the planes and we've mapped that plane over here, and then I looked at the equilibrium of that wedge, and the equilibrium of that wedge required looking at a problem where I had an arbitrary normal stress, and now that stress I'll just indicate with sigma prime. It's not necessarily x, because I know that if I choose not this plane but a plane with orientation that plus pi over 2, so here the orientation is arbitrary theta, so if I choose theta plus pi over 2, it would send me to that plane, which is sigma y prime. So I'm just going to put sigma prime, and I understand that there is only one shear stress we're talking about. Let me just call it tau prime. Okay? So in general, there's a normal stress and a shear stress, and the way I get it is from the equilibrium of the forces. There is a sigma y there is a sigma x, and there is a tau xy. And from that, I get everything that I need. All right, and the result delivers that the normal stress is equal to, let's write it over here, the normal stress is equal to sigma x plus y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. And there is a tau prime, which is equal to minus sigma x minus sigma y over 2, minus multiplies everything, sine 2 theta plus tau xy cosine 2 theta. Great. Okay. Now at this point, maybe I should highlight something. So in the previous topic, we talked about isotropy, anisotropy, elasticity, etc. or thermoelasticity for that matter. So Now, we're doing something with which we can calculate the way the stress looks on different planes, okay? The components of the stress with respect to different orientation of my axis, with respect to different orientation of the small element. All right, good. So now that description, those calculations, those discussions are based on equilibrium. I calculate these through equilibrium. And equilibrium doesn't care whether I have elasticity or thermoelasticity, isotropy, anisotropy, and so on. So everything that we've done so far is valid for any state of stress, irrespective of where it comes from. Could be associated with an anisotropic material, isotropic material, elastic, thermoelastic, whatever, right? So you give me a state of stress and I can tell you, well, how its components look, how the normal and shear stresses look, what their values are on other planes, right? On a different geometric picture, okay? And that is based on equilibrium alone. That's why it applies to any kind of material behavior. Now that I understand the range of validity, which is quite range for these equations, I'd like to put them in a form that is more manageable, easier to remember. And for that purpose, what I'm going to do is, I am going to simply start with these expressions, and I will take the normal stress. In fact, let's also drop the primes. So this is a normal stress that is associated with any choice of the directions. So just to make things a little bit more convenient with respect to our upcoming notation. Okay, I do understand this to be x prime, and this is tau xy prime, and this here is sigma x prime, tau xy prime, etc. I just call them normal stress and shear stress, and we understand that the values that they can take eventually, particularly when we reach the principal stresses. So I will take sigma, and from sigma I will subtract this portion. So let's write minus sigma x plus sigma y divided by 2. Okay? So then I will square it. So that minus that is equal to this value, and I'm going to square it. And then onto that, I am going to add tau squared. Now, if you do that calculation, right? So if you do that calculation, you will have, when you square this, you will have terms like cosine squared, sine squared, and cosine sine. And here you will have sine squared, cosine sine. The cosine sine terms, one is a plus, the other one is a minus. The multiplying terms are the same. When you sum them, they will cancel. Cosine squared sum to 1, sine squared sum to 1. And you end up with, do the math yourself, a final expression that's only appearing in terms of those factors, namely sigma x minus sigma 1 y over 2 squared plus tau xy squared. And now when you look to this equation, what you see is a quantity, or if you like, think of sigma as x-axis, tau as y-axis. X minus a certain value squared plus y squared is equal to something. Let's call that something r squared to make it more suggestive. So it's like radius squared. Radius of what? Radius of a circle, because now this becomes the equation of a circle. X minus, if you like, let's call this a, the center of the circle. The center of the circle is at x equals a, y equals 0, because this is like tau minus 0 squared. Tau is like y, so it's a equation of a circle. So because it is the equation of a circle, now I know that I can somehow express the, or indicate the set of normal and shear stresses associated with some arbitrary rotation theta from the original picture to this rotated picture. I can express any value of sigma and tau that's associated with that with a circle picture. And just I need to now go ahead and draw that circle rather carefully. The radius of the circle is the square root of that, and that should be the center of the circle along the x-axis. So the way we are going to draw that circle is going to be based on a few conventions that will allow us to make clear deductions in the relation between the circle I'm about to draw and that picture. So the circle, first of all, the x-axis is like sigma, or the tau axis is like y. So I'm going to draw a coordinate system for the circle, for the purposes of drawing the circle, where the x is sigma and the y is tau. Okay, that's going to be my choice. And well, certainly you could have switched those roles, but that's going to be our choice. Now, the circle is x minus a squared tau y minus 0 squared, if you like. So the center is going to lie on the sigma axis, on the x-axis. I'm assuming presently that, notice, it's plane stress, but also I'm going to assume that sigma x is larger than sigma y. Okay, that's going to be my assumption as I draw that picture, which are both going to be greater than 0. And I'm going to also assume that tau xy is greater than 0. Okay, and this is not a necessity, it's just that I need to make some conventions when I draw the circle, and that circle initially, because I don't have numerical values, is going to be based on these assumptions. If there are additional assumptions, I'm going to also state them. So these are in red, but again, they will be dropped shortly. It's just that the conventions always apply, but the particular picture rests on some assumptions. So with that particular picture, for instance, both are positive, so the value of A is positive. So the center of the circle is going to lie here. That circle will have a radius, which is the square root of that, right? So I'll just go ahead and draw a circle with that radius. So now the radius could be so large that the circle is perhaps like this. It goes into the negative sigma values. I'm going to assume also, without writing it, the radius is not that large, so that eventually the radius of the circle keeps the circle in the positive sigma region of our page, okay, of our coordinates. So the circle is going to, let's say, look like this. Okay. So that circle, when we draw it, is called the Morse circle. Okay. But let's be a little bit more careful about how to draw it. So first of all, that point is A. Okay. The radius of the circle, it is going to be R. Okay. And what we are saying is all the possible choices of theta have associated normal and shear stresses, and those normal and shear stresses are such that they satisfy the equation of the circle. In other words, for all possible orientations of this red picture, I will have normal and shear stresses which satisfy the equation of the circle, and therefore if I put a point that represents a state of stress associated for this given state of stress associated with a certain orientation, that's going to be a point sigma tau, and that sigma tau point somewhere, it cannot be here, it cannot be here, because it needs to satisfy the equation of the circle. It has to lie on the circle. Every combination will give me a new, every rotation will give me a new sigma and tau value associated with a different orientation, and all of those values ultimately lie on the equation of the circle. They satisfy the equation of the circle. They have to lie on this green line. Now, therefore, the original components of the stress with respect to x and y also have to lie on that circle. The original point, the original state of stress, has two sets of points. Now, let me slowly indicate that. First of all, there is a x point. The x point, just like any other orientation, will have a normal and a shear component associated with it. There will be a normal stress component and a shear stress component. I can put here a plus or a minus. It doesn't matter. Eventually the squares go into this picture, if I put sigma x instead of sigma and tau xy into this equation, it is supposed to satisfy this equation. Does it? Well, tau equals tau xy, this term is equal. If this is sigma x minus that, it's this value minus, but there is the square and therefore the equality holds. So x point does satisfy this equality. Likewise, I can pick a y point that also satisfy this equality. So sigma y plus or minus, I'm going to comment on the signs shortly, tau xy. Likewise, you can put that also over here and you'll see that it is identically satisfied. Now, however, these 2 points are associated with 2 different planes that differ from each other by 90 degrees. Okay, so they are going to correspond to different points on this circle, because to reach a certain value, if I give a rotation of theta, to reach the other plane that's perpendicular to it, so to go from here to there or there to there, I have to rotate by an additional on the original picture here by 90 degrees. So when I rotate, I move on the circle. So if one point is here, the other one is going to be somewhere else. So these are 2 points that I need to map onto the circle. Now, as I do that, I'm going to pick the following convention. I am going to put always the x point with a minus sign. This is a very important assumption that you should keep in mind. And the y point goes with a plus sign. Okay? Now, it is minus tau xy. Tau xy itself might have a negative value. So if this is tau xy is minus 10, another minus, it will make plus 10. Okay? So here I'm assuming that tau xy is positive, therefore this is going to be a negative value. That's going to go somewhere here. I don't know where. It depends on the values of sigma x and sigma y. Let us, and also tau xy, let us assume that it goes there. Okay, so it has to lie on the circle because it's just one normal and shear stress combination. So this is the x point, which is sigma x minus tau xy. And the other point is sigma y plus tau xy. So if this distance is tau xy, the other distance where this lies is plus tau xy. Now the center is sigma x plus sigma y over 2. Okay, so if you look at the distance from this to that point, it is sigma x minus y over 2. The distance of sigma y to that point is also supposed to be sigma x minus y over 2, right? You subtract that from that, it's the same value. And since sigma y is less than sigma x, it's not the same, it has to lie to the left. The distance has to be the same, and therefore that point will be over here. Okay, so these are just guides. So the real point is going to lie there. This is the y point. And that is sigma y plus tau xy. And so the diameter of the circle is right there. Okay. Well, what was the radius of the circle? The radius of the circle was equal to the square root of that. So it's equal to square root, let's write that explicitly, sigma x minus sigma y over 2 square plus tau xy squared. Great. Okay, I'll come back to this minus sign issue. Okay, I put for the sake of being complete, I put a plus here. Of course, it is obsolete, but I put it there anywhere to distinguish these 2 choices from each other. Okay, right. That's our Morse circle now. So actually, the way we draw the Morse circle is not exactly in this order. The way I would normally draw it is, first, I would always know that this is the most important piece of information that I should keep in mind. Where to put the points, and everything else follows from that. So I'm going to go ahead. The way I would normally draw it is, I look at the state of stress, I write the x point correctly and the y point correctly. And then I go ahead and put them on my map. I'll call it the map often. It's on the sigma tau axis. Okay? If you put these in the correct places, then you know their values, and then you draw a line through them. That is along the diameter. where it intersects, that's the center. Well, what's the center? It's the x value times plus the y value divided by 2 because it's right in the middle. It's the mean of the two values, okay? So that's easy. And then I want to calculate this radius. It is this distance, which is sigma x minus the center, that value squared, plus that distance squared, tau xy. That's tau xy squared, square root. That's the radius. So it's very easy to remember, right? And now, moreover, once you have that, you can determine right? You know the radius. You know where that circle is going to intersect the horizontal axis. Let's keep those in mind. And then you can complete your circle. Now, that's the way I would draw it. Starting here and then putting these points, connecting them, finding the center, finding the radius, finding out where they cross the sigma axis, and then completing the circle. Those are the steps, right? Now, once I do that, there are a few things that I can immediately observe. Observation number one. Observation number one has to do with the principal normal stresses and the rotation that's necessary to reach that plane. All right. So, first of all, what am I finding out on this from this circle? This circle tells me that originally you have that picture, and that picture falls onto these points within the circle. Okay. Now, what I can think of is I can think of this diameter as a dial. The original picture locates the dial in this location, and I know that the value of sigma x is this value, the value of tau xy is minus that value. Likewise for y. Now, when I rotate this picture through an angle of theta, I will be moving on the circle. Every time there will be two normal stresses that differ by each other in terms of orientation through 90 degrees. Apparently, on the circle, that difference is amplified by a factor of 2. Here, to go from one plane to the other, it's pi over 2, 90 degrees. Here, to go from one to the other, from x to y, it is pi or 180. Okay. Now, which means that somehow, if I wanted to start from the original picture and rotate by a certain amount theta towards some other picture, that amount of rotation is going to reflect twice as much onto the Morse circle. Okay? Onto the Morse circle, it will reflect twice as large. So in other words, if I rotate through an angle theta on this picture, I am going to eventually move through an angle 2 theta, okay, to a point where now I have a new normal stress value, sigma x prime, a new shear stress value minus tau xy prime. Here I would have sigma y prime and plus tau xy prime. Let me again put the plus. This is the x prime point. Okay, and this is the y prime point. In other words, this is the stress component associated with that surface. Those are associated with that surface, associated with this picture, in other words, right? I've rotated through an angle theta, and now on the Morse circle, I'm rotating through an angle 2 theta. Why is there this factor of 2 once again? Well, actually, ultimately, it has to do with the fact that the equations always involve a factor of 2, and I derive my interpretation of the circle from these equations. And in the equations, a rotation of theta reflects as 2 theta, and therefore the rotation of theta on the original picture reflects as a rotation of 2 theta on the Morse circle. Again, how do I see that simply? Well, on the original picture, if I want to go from x prime to y prime, I just have to go through an angle of 90 degrees. And here, on the other hand, I go through an angle of 180 degrees, right? Amplification of 2. This is the second thing you have to always keep in mind. This is critical. So always keep in mind the factor of 2 theta that appears in the equation and likewise in our Morse circle. So now what our Morse circle is able to give us is you start from the original picture and you can determine the components of the stress with respect to a rotated picture for the same state of stress, just a rotated picture, by doing a corresponding rotation on the Mohr circle, but that rotation is just twice as much. Okay, so therefore, so I can rotate this dial in any location towards any location I want, and I can easily calculate the new components of the stress by following trigonometric identities combined with some simple geometry, some simple algebra from the location of the points and the fact that they lie on a circle. So given this angle, given these original values, if I ask you the blue circle values, the new values, you can easily calculate them. Maybe not too easily, but in principle, with some effort, without having to memorize anything, in particular without having to memorize those equations. But among all of those values, there are a set of values that are in particular important. So for instance, suppose I rotate to a particular picture where I move so much that tau xy is 0. What is that point? That point is exactly this point. Let's mark it in green. Okay. Now, what is special about this point and the corresponding position of the dial? Notice it's this one. Okay. So sigma x was sigma x prime with a certain shear stress, and now I've rotated so much that there is no shear stress. How do I know that? Well, I'm at tau equals 0. And so this must be a principal value, right? Principal normal value. And that value, I'm going to rotate from x to x prime to sigma 1. That value is going to be sigma 2. Well, what is sigma 1? It is supposed to be a plus the radius, and sigma 2 is simply supposed to be a minus the radius. A is the mean, the radius has that expression. Now we may want to go back and recall some of these equations, right? So a plus r, the center plus the radius, that's where it is, right? Or a minus the radius, that's where it is, right? So it turns out, right, based on this convention of the Mohr circle, now I don't have to memorize any equations. I don't have to keep these in mind. Now, rotation from green dial to the blue dial, arbitrary location, will rarely be of interest to us. In fact, in the context of this course, we're never going to do such an exercise. But rotation towards the principal direction is going to be very important, and that's very easy to do because once I know the center and the radius, and I draw the circle, I determine those points anyway. And boom, you have it. And well, what is this angle over here? Well, that angle is associated with the rotation to the principal normal directions, which is not theta n, remember, twice theta n, okay? Now, once you reach 2 theta n, the principal plane, if I rotate through an angle of pi over 4, I know that I reach the plane with maximum shear stress, the principal shear stress plane. And on the Mohr circle, I rotate twice as much, so that's going to be a rotation of 90 degrees, not 45 to reach shear stress, max shear stress or principal shear stress, but twice as much on the Mohr circle, and therefore the rotation is going to take me up here, and indeed you see that the shear stress has become a maximum. And at that point, and let's now plot that in some other color, let's say black. So I'm going to be up here, and the dial now is like this. So my dial was originally like this, and I rotated from the original picture to the principal picture, and now from the principal picture, again through an angle of pi over 4 or 45 on the original system, physical system, but twice as much, in other words 90 on the Mohr circle, towards the principal shear stress planes. And here I have a point which is equal to a plus the radius and a minus the radius. And I know that on the plane with maximum shear stress, principal shear stress, I have a plus and a minus value for the shear stress, which is equal to exactly this value, plus minus that, and the normal stresses are the same, and they are both equal to A, as they should be, right? So everything is aligning, so this angle over here is equal to rotating from the original picture 2 theta n plus twice as much, 90, or 2 theta s, right? Theta s and theta n differ by 45 degrees, takes me to the maximum planes with principal shear stresses. So we've put everything on the same picture, on a single circle, with which we are able to predict anything that's associated with the principal directions, whether it be normal or shear values. In doing so, I highlighted two so far important things. One, you start from this. You get this right, put them on your map correctly, draw your dial, identify the center and the radius, and then complete the circle. Everything else follows in a straightforward fashion. You just have to always remember that the amount of rotation on the Mohr circle is twice the rotation on the physical system. Okay? That follows from your equations. And everything we've drawn is consistent with that. And finally, there's one more thing we want to now comment on. Why did we put a minus sign there? Now here you see I am rotating in the clockwise direction, and if I do everything like this, if I rotate also in the clockwise direction, I reach a plane with maximum normal stress, which is associated with the rotation of x. In other words, if I have a picture that is consistent with these assumptions, if I rotate in the clockwise direction, I expect sigma x to increase and sigma x prime increases further towards sigma 1, right? So for that to occur, so in other words, if I look at the Mohr circle, if I plot everything like this, I'm predicting that if I rotate in the counterclockwise direction, the sigma x value is going to increase towards the principal direction. If I want to predict that correctly, that's what turns out to be from the mathematics, right? You want to plot sigma x together with a minus sign, because otherwise what will happen is, first of all, let's agree. If this is a minus, then this is a plus. If this is a plus, this must be a minus. So if I put this point over there, the other one must be over here, because they need to differ by 90 degrees on the physical picture or 180 on the Mohr circle. So either this or that. But if I were to plot it like this, then that would mean that for a rotation essentially of clockwise value on the physical picture, I would have to rotate in the reverse direction to make sure that sigma x is increasing towards sigma 1 in the reverse direction on the Mohr circle. So with this choice instead of that, which requires that I plot sigma x with minus tau xy and y with plus tau xy, it allows me to conclude that the direction of rotation on the Mohr circle is the same as direction of rotation on the physical system. Okay? It's just that the amount is twice as large as the physical system. Okay? And always, again, keep in mind, nothing is really rotating physically. We're just picking planes with different orientations so that I can ultimately find where the normal stress is at maximum, where the shear stress is at maximum. And why do I want to do that? Because I am searching at a point in the structure what those critical values are, normal or shear stresses, because the material fails according to a function of those stresses. And the Mohr circle is helping me identify those values in a compact fashion without having to memorize anything. So next, let's go ahead and solve a few examples to demonstrate these ideas.